give you back like at least 20 minutes so you can leave early, but mostly. Okay, so last class, we just talked about matrix stuff. So we talked about the operations we can do on them, specifically addition, subtraction, and scalar multiplication. Super riveting stuff. It was exactly how we expected it to be, and nothing was that weird. And then we sort of finished off talking about matrix multiplication, because that's something we can actually do with matrices instead of vectors, where we can't. And that one ends up being interesting. So kind of funny about math. When things don't work out well is when math is actually worth studying. Because, you know, this was a really hard thing to dispel from my mom when I was like, yeah, Mom, I'm going to, my undergraduate degree is in mathematics and I'm going to grad school for it. And, you know, her whole life, she's like, oh, you're just learning to do arithmetic. I'm like, Mom, you can do arithmetic. So no, I'm not going to school for that. Because arithmetic it works, right? Everything works nice. It works how you'd expect. You add numbers and they work how you want. So math really starts to get interesting when you can ask the question, oh, that doesn't work how we expect. Now what, right? And then you discover why and when and the conditions on it and what does that lead to. And matrix multiplication gives you a taste of that because that's really what happens. But one of the things we can do is we can talk about matrix powers. So these do fortunately behave how you would expect. So we're going to say that if you take a to the power 0, that's the identity matrix. So this matches, I'm going to write like next to it numbers, right? For numbers, this is the equivalent thing that we would write. Okay, so then a to the power k, that's just a times a times a k times. So just like with numbers, right? X to the power 5 is x times x times x times x times x, right? A to the power 4 is a times a times a times a. But there is a condition here. This is going to be a whole number. So when we're talking about numbers, you know, x to the k, for numbers, this can actually be basically anything, right? We can talk about x to the 1/2, right? That's the square root. We can talk to x to the -2. I'll mention what that means when we get there, but that's something that makes sense for numbers. For matrices, not so much. We're going to stick only to positive whole numbers for now. But the point is, this works how you would expect. So one of the reasons why we're talking about matrix multiplication and then matrix inverses, another way to write equations. So we can actually write equations in terms of matrix multiplication. So let's just say, you know, in my notes, I have the gross stuff. I'm just going to give you an example because that will show you what we want. So I'm going to write down a random equation like this, right? So we've got this equation. So if we wanted to solve this with the techniques we've talked about, then we would just find that augmented matrix and do our row reduction and all that stuff. So that's this thing. 2, 3, 1, -2. We draw this line. And we write this. So this chunk right here in our definition was A, and this chunk here was B. So we can tweak this a little bit. We can basically do the same thing, but we're going to try to use matrix multiplication to describe this instead. So we're going to say it's A equals B, but there's going to be something extra here. So this is this same A. This is the same B. So what are we going to say here to make it have to do with matrix multiplication? We're going to create a new vector called X. So what's in here? It's a vector of our variables. That's it. So in this case, it would be xy, right? So this is called the matrix form of an equation. Now let's turn to this example right here so I can show you what I mean. So we've got A, which is this matrix, times x, and what I'm saying is this is just a vector of our variables. So what are our variables? X, y. And this equals b, which is 1 minus 1. So this corresponds to our equations, right? Because this is 2 times x plus 3y. 2x plus 3y is our first entry. X minus 2y has to equal this. But now we just look at this. This thing has to equal this. 2x plus 3y equals 1. That's our first equation. X minus 2y equals minus 1. That's our second equation, right? So these are capturing the same information. But this way of writing it will end up being useful because just think about equations with numbers, right? If you had 5x equals 3, you could solve for x by dividing by 5, right? And that will give you x. X equals 3 over 5. So our goal is to try to do something similar here with matrices. They don't work out quite as nice, but they work out almost as nice. So let's talk about some properties. So addition, good news, works how we hope. So that means there's no funny twists. So like a plus b equals b plus a, stuff with brackets, a plus b plus c is equal to a plus b plus c. Distributive property with numbers. So you've got some number here, s, a plus b is sa plus sb. Basically, everything here works how you'd hope, right? There's nothing like if you think based on how it works for arithmetic, it probably works here. Okay. I guess there's one other one. The number 1 times a is a. So what about multiplication? So good news and bad news. Most of the things also work how you would expect. So an example is brackets. It doesn't matter how we write them or even if we do. That's what this is saying, right? It's saying, hey, you could multiply b times c and then a, or you could do a times b and then c, right? It doesn't matter in which order you perform these multiplications. That also works over addition, how you would hope. So a times b plus a times c, right? This distributes how you would hope. That's good. So that corresponds to this. The identity times a is the same thing as a times the identity, which is a. So I mentioned this matrix here, that identity matrix, behaves like 1. Okay, so this corresponds to this, this corresponds to this, this corresponds to this. Something's missing, right? I didn't write this down. I didn't write a times b as b times a because it's not. That's not the case for matrices. In fact, it's almost never the case. So if I write down 2 random matrices, it won't work out. So that's exactly what I'm going to do. So is a times b equal b times a? Well, let's let a equal. Give me some numbers. I don't care what they are.
2.
Sure. 2. Give me another one.
7.
Let's do minus 1 and 3. B is equal to, I don't know, pick a number again. 0? Sure. Let's do minus 1. What's a number that's not here? Let's do 10?
9.
9? Sure. No, nines and sevens. And then let's do 2. Sure, right? Like, people help me build these. If A times B is B times A, then I'll go buy a lottery ticket. Because the amount is like 80 million right now. Surely I'll win. So let's perform this multiplication. So we're just going to do the good old-fashioned finger movement. So hopefully I have room here. 2 times 0 is 0, plus 7 times 9, so 63. This is minus 2 plus 14, so 12. 0, 27. Minus 1 times minus 1 is plus 1. Then this is 6, so 7. The first one. All right, let's see what B times A is. So that's 0, minus 1, 9, 2. 2, 7, minus 1, 3. All right, what do we get? 0 times 2 is 0. Minus 1 times minus 1 is 1. Okay, I don't even need to go any further to show you that this isn't the same thing, right? Is 63 the same thing as 1? No. So already, literally the first number, they're not the same thing. But we'll just keep going to practice the multiplication. So 0 times 7 is 0. So that's minus 3. 9 times 2 is 18. Minus 2, so 16. 9 times 7 is 63. Plus 6 is 69 there. So not only do none of these numbers match, there isn't even any like repeated numbers, right? Like it's not even like 63 is here and then it's 63 down here, right? Like they're all completely different. So these couldn't be further from each other, right? So A times B does not equal B times A. So that's something very, very important to know about matrices, because in all of these operations and structures that we've talked about, you know, we've taken this for granted, right? A intersect B is the same thing as B intersect A. A and B is the same thing as B and A. A times B for matrices is not the same thing as B times A. And actually, this condition being violated causes essentially a domino effect. There's sort of a lot of stuff that goes wrong here. So I don't know if I should call it properties or weirdness. But we're just going to talk about them real quick. So various things that you take for granted for numbers fall apart because of this. So if A times B equals 0, well, let's just think, right? If we have numbers, so if we had x times y equals 0, what can we say about x and y if they're numbers? So two numbers being multiplied together equals 0. Yeah, one of these numbers has to be 0, right? So if we have two numbers multiplied together equals 0, one of them has to be 0. So either x is 0 or y is 0, right? So if two matrices multiplied together are 0, they don't have to be 0. It's not the case that A equals 0 or B equals 0, right? There are non-zero matrices that you can multiply together to get 0. So I have, like, some of the examples I have constructed are very, very simple, but there are non-simple examples. If someone's like, hey, I still don't believe you because you constructed a simple example, I'd be like, okay, I'll just go find one that doesn't work out. And then it is like this. So yeah, okay, they're simple, but importantly, they're not 0, right? There is something in each of these matrices that is not 0. So even though they're simple, they're non-zero. So A times B. What's that? Get this. 0 plus 0. 0 plus 0. 0 times 0, 0. 0. 0 times 0. We got the zero matrix, right? I mean, of course, that's going to be the case because that's what I, actually constructed this to be. But this is not 0. This is not 0. We multiplied them together and got 0, right? As a consequence of this, the cancellation property doesn't hold. Property doesn't always hold. So what I mean by that is if A times B equals A times C, it does not mean that we can cross out the A's and get, or divide by the A's and get that B equals C, right? That's not the case. It's a consequence of this. I have it written down in my notes. You basically move this over. So you have AB minus AC, factor out the A, you get A times B minus C equals 0, which means it's not guaranteed that B minus C equals 0, aka B equals C. But the point is, this isn't true either, right? This is true for numbers, right? If you think like 5x equals 5y, cancel out the 5's, and you get x equals y, right? For numbers, right? This doesn't hold for matrices. It's not the case. Okay, but there are some weirder properties that sort of come out of this. So there are matrices that aren't 0. A to some power equals 0. So we think about that. You take some number, like 5. If you raise it to any power, it's not going to become 0, right? Doesn't matter what you raise it to, it's going to stay a number, and that's not 0. The only number that when you raise it to a power gives you 0 back is 0 itself. Everything else will just give you some other number. What I'm saying is there are matrices that are not 0 where that's not the case. So an example, again, I'm calling this one quote unquote simple, but from a theoretical perspective, matrices of this shape are actually anything but. They're extremely important. Another example of a matrix that would look like this is, let's say, 2, 3. That's another one. So this matrix would also satisfy this property. But let's just see what happens with this one I have written down here. So we're going to say, what's A squared? Well, that's A times A. Like this. Okay. Plug and chug. 0 times 0 plus 2 times 0 gives us 0. 0 times 2 plus 2 times 0 gives us 0. 0 times, that's just 0 and 0. 0 times 2 plus 0 times 0 is 0. So we got 0 out of it. So this is a non-zero matrix that when we square it, gives us 0. Again, this one here, you look at it and you're like, yeah, but that's like a really trivial, simple example. So no. This is what's called a Jordan block, named after Jordan. No, it's a mathematician named Jordan. I think it was French. But anyway, these types of shapes are everywhere in matrices. Like if you're working on physical problems, you will run into these. But this thing happens so often. The idea of a matrix being raised to some power and giving us 0, we give this a name. These are called nilpotent. Nil for 0. And potent because, I don't know. I assume it's from German or something, meaning raising it to a power or something like that. when it comes to these names, no, I don't expect you to memorize this or anything. I mean, I don't expect you to memorize anything, but like if I want you to work with a nilpotent matrix, I'll be like, hey, as a reminder, this is what it means. Even on an assignment question, so you don't have to dig through your notes to find it. But the point is, I mean, we gave stuff of this a specific shape, a name. So they come up all the time, which means these come up all the time. So we gave it a name. Okay, so there's another one. That's also kind of weird. And this one, fortunately, is, I cooked up an example that isn't super simple looking. So there are matrices A, which are not 0 or the identity, where when you take A and you square it, nothing happens. You get back where you started. So I think this is 4 minus 1 and 12 minus 3. That looks like I'm subtracting the entries. Like that. So what happens if we square this thing? Well, that's A times A. So this thing times itself. 12 minus 3. Okay, so what happens? 4 times 4 is 16. Minus 1 times 12 is minus 12. 4 minus 12 is 4. Or 16 minus 12 is 4. 4 times minus 1, so that's minus 4. Minus times minus becomes positive. 3 minus 4 plus 3 is minus 1. 12 times 4 is 48. Minus 3 times 12, 36. So 48 minus 36 is 12. Minus 12 plus 9 minus 3. So nothing happened, right? We multiply this matrix by itself and got back where we started. So when we think in terms of numbers, there are also only two numbers where this is the case, right? 0 squared is 0. 1 squared is 1. If we take any other number and square it, it changes, right? We either lose the minus sign, so all the negative numbers are out. If we take anything bigger than 1, it gets even bigger. If we take anything smaller than 1, it becomes smaller, right? So squaring it changes the number, but not for matrices. There are matrices where that's not the case. So this is called idempotent. Again, don't worry about it. I like to write it down because my math nerd brain won't let me not tell you what it's called. And what in math, again, we name all these things not because we like to confuse new students or anything like that with a bunch of terminology. It's because it comes up often enough that, you know, if we had to write, hey, let A be a matrix that's neither 0 nor the identity where A squared is equal to A. If we had to write that all the time, that's a mouthful, right? So we just say, let A be an idempotent matrix. Right? It just means this. It means that if you square it, you get back where you started. But the point is, there's lots of kind of weird stuff here, right? There's another one. It's in my notes where A squared will equal the identity, right? A times A is basically 1. So think of numbers, right? The only 1 times 1 is 1. Minus 1 times minus 1 is 1. But for matrices, there's lots of different examples that aren't that. So they're self-inverses is what we call those. So the point is there's lots and lots and lots and lots of different things here. So actually, do I want to talk about that? I will talk about that on Wednesday if I need to. I don't think I need to, though. There's also properties of transpose that basically says they work how you'd kind of hope to. They're nice as well. So, okay, with multiplication, though, it doesn't work super great. There's a lot of problems. You get these weird situations, and it's all because that commutative property doesn't work. A times B is not B times A. But because of that, we had this problem, right? This property doesn't hold. We can't just sort of divide by a matrix and cancel it out. So then this is what I mean, where when stuff breaks in math, that's when it becomes interesting, because we start asking questions. We're like, okay, yeah, you know, from this isn't guaranteed, but is it always not guaranteed. Like, does it fail every time, or are there situations where it works? So that's what we want to answer is, hey, where does stuff like this work? And so that needs inverses. And that is a word that you probably, if you took Math 30-1, you would have maybe heard it in passing because, like, the square root with a domain restriction is the inverse of x squared. But mostly it would have been swept under the rug. But it turns out inverses. The idea of using an inverse is something that you've been using since, God, when did we learn fractions? In like grade 5, grade 6? I don't know. Since then, right? You've been using this concept behind the scenes. It's just we didn't call it that. So we're going to first start with a definition. And then I will relate this concept to numbers. So let A be a square matrix. It does have to be square. Then a matrix B an inverse of A if A times B is the same thing as B times A. Okay, well, that's already nice. We know this isn't normally true. And both of those just give you the identity matrix. So they cancel each other out, basically. So this inverse is actually unique. And we denote it. Well, if it's unique, we don't want to just call it B, right? We want to connect it to A. So we'll use A to the minus 1. So that means this property we would instead write as A to the A inverse A equals I, right, using this notation. So why did we choose this notation? Well, again, if you took 30-1, then this is something you've seen, but it probably went in one ear out the other because you never used it. If you took 30-2, you probably didn't see it, but that's okay. I'll explain it. So this notation here to the -1 is something we actually use for numbers too. So you would have in 30-1 seen x to the -1 as a function. But let's not talk about functions. Let's talk about numbers, because we can do this to numbers too. So what this notation is saying is just, hey, take this thing and write the reciprocal, or 1 over x. So this is 1 over 5, right? And we can kind of see this notation is connected to this, right? Because 5 to the -1 times 5, same thing here, equals identity, or 1. So we know this is 1 over 5 times 5. They cancel out, and we get 1, right? So that's the motivation for this definition, is it actually came from numbers, right? There's this connection here. We do this all the time in numbers, right? We divide by 5 and cancel stuff out. So this is supposed to be the matrix analog of doing that. So let me just do an example real quick of showing you that, hey, these do exist. Because I've sort of been casting doubt on matrix multiplication. I've been like, hey, it's kind of bad. But it turns out, no. This is a saving grace. So let's let A be the following. 2, 3, 1, 2. And then we're going to say, hey, A inverse, we're claiming, is this. So we can check these are inverses by just multiplying them together, right? A times A inverse had better give us the identity. And this property says you can do it in either order, so write it down however you want. -1, 2. All right. 2 times 2 is 4. -3 is 1. 2 times minus 3, so that's minus 6, plus 6, 0. 2 minus 2, 0. Minus 3 plus 4, 1. Right? So this here is the identity. So indeed, these are inverses of each other. So if an inverse exists, we say a matrix is invertible. If A inverse exists, we say A is invertible. Like less cool convertible, I guess. Is that a good joke? Did I do it? Yeah, okay, fair. I deserve that. Okay, so great. We have this concept here, and with this explanation, we can kind of see how it would be useful, right? It sort of gives us the ability to, in some way, divide by something. There's a bit of a problem with calling it that, but we'll get there. There's a bigger problem here, and that's that, this just says, hey, yeah, I just showed you an example of, here is one. How do we find it, right? Okay, well, fortunately, for 2x2 matrices, there's a formula. And we love formulas because, one, easy to use, two, easy to implement in programming, right? You just have a formula, you have variables, you plug them in, boom, done. So, if A is the following matrix, so it's just your usual 2x2, then A inverse, so we basically just shuffle the numbers around a bit here. So we swap the diagonals. So these two swap. And then we just put minus signs in front of this. And that's it. Except there's a bit of an extra fudge factor here. So there's this extra number here. We're dividing by it. AD minus BC. Now this thing right here, it doesn't matter too much. This is called the determinant of a matrix. And I could spend like a month talking about determinants because there's so many properties of it. Think of it like when we talk about vectors, I was like, hey, here's this funny new thing we can do to vectors. We could do a dot product. This is sort of an analog for matrices, right? You've got a matrix and okay, there's this funny thing you can do to a matrix. It's called compute a determinant, which is just a number corresponding to it. We're not going to talk about it. But the reason why I'm pointing this out is there's this number here. And I'm saying, hey, you want to find the inverse of a matrix? You're going to need this number. So we're dividing by it. If this number were 0, we have a problem, right? Because then we'd have 1 over 0 and this matrix doesn't have an inverse. So that's the situation where it doesn't work. So if AD minus BC equals 0, no inverse. And now that's why this is kind of nice, because if we're looking at it and we're saying, well, when does that cancellation property hold? Well, we're going to say when a matrix is invertible. So then we'd say, okay, well, when is one invertible? Hey, it's only not when this is 0. So this is one number where it doesn't work, 0. So that means there are infinity possibilities where it does work, right? So it turns out most matrices are invertible, right? Most of them, we will actually get the cancellation property to hold. So it is something we have to be careful about, but most of the time it works out nicely. Well, nicely in the sense of it's possible. As you can see here, this could be a pretty gnarly looking fraction. So you might end up with gross looking numbers. So the reason why we care about this, as I've been sort of hinting at, is that it gives us kind of a shortcut for solving systems of equations. So we're going to combine that idea of matrix form of an equation and these inverses to give us a shortcut to solve systems. So if A is invertible, And we have the system AX equals B, then, well, we could solve this. We can multiply by A inverse on the left. And this is something that you have to pay attention to with matrix multiplication. You have to specify that because A times B is not the same thing as B times A. So if I do it from the right, then that's a different result, right? So you do have to specify this. But what happens if we do this? So we're going to take this equation, right? It's just an equation. So if we do something to one side, as long as we do the same thing to the other side, we're in good shape. So we have A inverse times A times X is equal to A inverse times B. Okay, but this stuff right here we know is the identity, right? This is they cancel out. And the identity times anything is just that anything. But now, when we're trying to solve an equation, the goal is to just say, hey, the variables equal something, right? This right here is a vector that holds all of our variables, so x, y, z as an example. And this is saying, hey, x, y, z equals something, right? This is just going to be a vector of numbers. So this gives our solution. So hey, if we know this inverse, then great. Now we can skip row reduction, right? Because look, right here, we have a formula now for finding this inverse. So essentially, we now have a formula for solving a system of equations. For a 2x2 system of equations anyway. So 2 equations, 2 variables. So good news and bad news. Good news, this seems like it is a method that lets us skip doing row operations, right? Because the way we would solve this system before, so we have a system of equations, we would augment and row reduce, right? We do that row reduction stuff. Which, by the way, I looked at the last 2 quizzes. I need to post the grades for them. Everyone did fine on that, right? Like everyone did a great job of doing row reduction. So, okay, that saves us some effort. But bad news, we need to find this thing. And the best way to find it is row reduction. So yes, this saves us row reduction, but no, we have to do the row reduction. So why would this actually matter? Well, there are lots of situations where this part stays the same, right? You're dealing with a physical system as an example. So think of it like this tells us how something moves through space, and this tells us where we want it to end up. So the thing that changes is, where we end up. It's a point that we're just moving around space. So if this is the only thing that changes, then we just have to compute this a bunch of times, right? So we do all the work to find A inverse, then we just do a bunch of multiplications and we get a bunch of different solutions. So that's why we would care about it. As a side note, I mentioned that this will still have to do row reduction. There is technically another way to find inverses. And this comes up, and this is for the video, and I guess everyone in here. So I haven't talked about it because it requires spending a lot of time discussing properties of determinants and why it works. So if you know how to solve a system, or you know how to find an inverse using minors and a bunch of cofactor expansions, do not do that. For 2 reasons. One, I didn't talk about it. So if you're going to do it, you better be able to explain in detail why it works and how it works, because I will grill you about it or I'll give you 0. And 2, it's actually worse anyway. It's a terrible method because if you have a 5x5 matrix, you now have to compute so many determinants, and it is exhausting to do that. So it's a bad method anyway. It's also computationally not very efficient. It's type safe in the sense of The only time you'll actually have to divide by fractions if your matrix contains no fractions is at the very end, but it's also inefficient in computers. So it's just not a good method. So row reduction turns out to be one of the more efficient methods. Anyway, okay, so what I'm saying is this lets us solve equations. So let's do an example. Let's actually practice that. We're going to start with a 2x2 system. So let's solve, and I'm going to have to write it down. 4x plus 3y equals 1, and 3x plus 2y equals minus 1. Oh, just a normal system. So you could augment and row reduce, right? You could find that augmented matrix, go through the row reduction, and you'll get your answer. That's totally fine. But let's try this approach. So we can read off what A is. 4, 3, 3, 2. We know what this B vector is, 1 minus 1. So now to get our solution, we just figure out A inverse and then multiply it by B. So what is A inverse? It's a 2x2 matrix. So there's a formula. So it says, essentially, A times D, so these diagonal things, 4 times 2, minus the off diagonals, 3 times 3. Swap the diagonal entries. 2, 4. Take these and put minus signs in front of them. That's it. There we go. That's our inverse. Well, we got this fraction to mess around with. So actually, I'm going to mess around with it on the side. So 1 over 8 minus 9 is 1 over negative 1, so it's negative 1. So we just have to take this matrix and multiply by minus 1. So that's minus 2, 3, 3, minus 4. That's our A inverse. So this method says, hey, just do A inverse times B. That's your answer. So A inverse times B gives us our X. So our A inverse is minus 2, 3, 3 minus 4 times B, 1 minus 1. So plug and chug. Minus 2, 3 times minus 1, so minus 5. 3 plus 4 is 7. There we go. So again, the reason why I mentioned that this technique is nice is because you don't have to do any more row reduction, or in this case, we just did a formula, if we change the parameters a little bit. So if instead I change this vector to be, say, 2, 3, I can do the same thing. I can say that's minus 4, 9, so 5, and 6 minus 12. There we go. There's the other solution, right? And so these are both, this is X and Y. Right? That tells you the X and the Y values that solve this system of equations. So this is pretty common in physics, where you would vary that right-hand thing, or when you're doing like rotations and stuff like that. Okay, cool. So that's how we find it for a 2x2 matrix, but of course there are bigger matrices than that, right? Sure, there's a nice formula here, but for anything bigger, there's not a nice formula. And like I said, we're going to use row reduction. So what about bigger matrices? So 3x3, 4x4, etc. So we're going to sort of leverage something we've already done before. So we're going to take this And we're gonna sort of use a similar trick. So we would augment and row reduce with the B vector. Instead, we're gonna put the whole identity matrix here. So that would look something like 1, 2, 3, 4, 5, 6, 7, 8, 9. We're gonna do an example of this, so that's why I'm just writing this down here real quick to show you what I mean. It will look something like that, right? So what we're going to do is we're going to say, okay, my goal is to perform row operations on basically just this left thing to turn it into the identity matrix. And I mean, this is one big matrix. So anything I try to do here will have to happen here too at the same time. But I'm not deliberately doing anything to this side. I only care about transforming this left-hand side. Right? That's my goal, is to work with that stuff. And so if we do this, there's sort of two situations that can happen. Oh, there's a hair there. Ew. So we can perform row operations on this, and either we're going to get the identity, or we're going to get not the identity. So that usually means there's a row of zeros. So the bottom row would be all zeros as an example. In this case, that's exactly what we want, because it turns out the exact same steps that would turn A into the identity turn the identity into the inverse. That's a theorem that I'm just spare you the details of. It's called, hold on, the fundamental theorem of invertible matrices. It states that A is invertible is the same thing as the reduced row echelon form of A is the identity, and you can use that to demonstrate this. So, blah, 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 who cares? The point is, these steps will turn it into the inverse. Now, in this case, though, you didn't get the identity. You got like a row of zeros or something like that. So what's here? Junk. Doesn't matter. It's all garbage. Because as soon as you get a row of zeros here, you can just say, not invertible. Why? Because that theorem says that we can reduce A to the identity, which means if this happens, we can't do that, which means it can't be invertible. So these are the two situations. So basically, we can answer two questions at the same time. If a question says, is this invertible? If so, find the inverse, then you do it either way. Either you'll hit here and you'll say, no, it's not invertible, or you'll get this and you'll be like, yes, it is. Here it is. Right? So the point is, more row operations, more row reduction. So let's just do an example, and that will kind of make it pretty clear what we're doing. I'm going to take up this whole space. So let's let A be the following matrix, and I have to be very careful. 1, 1, 1, 2, 0, minus 1, 0, minus 1. Find A inverse, if it exists, which, I mean, given the context, it does. So we set it up like this. We say, okay, just like with augmenting and row reducing, we do this setup. So we take A and put it next to the identity matrix. So what does that look like? 1, 1, 1, 2, 0, minus 1, 0, minus 1. And right next to it, 1, 0, 0, 0, 1, 0, like that. So now what we're going to do is we're going to do row operations to transform that matrix on the left into the identity, if we can. So basically, we're doing our normal row reduction, right? We're gonna go through the same steps as we always would, but now we sort of have this extra appendage coming along for the ride, right? So whatever we do here, we have to perform the same step over here because this is all one big row. But that just means we just focus on this. So if we want to turn this into the identity, we're going to go through the same process. We're going to say, okay, I want to make a 0 here and a 0 there. So row 2 will become row 2 minus row 1, and row 3 will become row 3 plus row 1. Right? That gets rid of that number there and that number there. All right, so we didn't touch this first row, but we did touch the second row. So we're subtracting this whole top row from this whole middle row. It's going to be 0, 1, minus 1. And now remember, we have to do the same thing to this side. So this minus this, oops, that becomes plus 1, 0. Right, we're just performing the same steps on that right-hand side. And now we're going to take this and add it to this. 0, 1, 0, 1, 0, 1. Well, you kind of see, it turns out there's not really anything conceptually that new here, right? We just put the identity next to it, and we're doing the exact same thing we've been doing. So now there's a couple choices here, right? We just perform the same steps. We say, all right, cover up this top row and repeat, right? So we want a 1 up at the top left. Well, there's two choices, right? This is already a 1, so that's good. This is sort of, in some sense, a nicer looking row because it already has zeros everywhere. My notes left it alone and just work with this. So just to present you with another one, I'm going to swap. I'm going to say row 2 swap with row 3. So we're going to get 1, 1, 1. We didn't change this top row at all yet. It's going to be 0, 1, 0, 1, 0, 1, and 0, 1, minus 1. Like that. We just swap them. So now, because I want to save board space, you could just go through the algorithm as normal, right? Create a 0 below, and then rinse and repeat. But I'm going to save some time here and say, well, why don't I just create a 0 above at the same time? Right? These are all 1s, so might as well. So row 1 will become row 1 minus row 2, and row 3 will become row 3 minus row 2. So we get 1, 0, 1, because that's a 0, so subtracting it from that does nothing. But now this changes. We subtract this from this, minus 1, like that. This stayed the same. This changed. 0, minus 1. And now we change this too. So this is minus 2, 1, minus 1. Okie doke. Now we rinse and repeat. We cover the top 2 rows. Oh, well, there's not really anything left to do, right? We change that to a 1. So minus 1 times row 3. What's that going to give us? 0, 0, minus 1, 1, 0, 1, 2, minus 1, 1. One more step. Create zeros above, and that's why I said I'll just do it earlier, right? Because, I mean, this is where you would do it if you didn't. So row 1 will become row 1 minus row 3. And look at that. We got the identity matrix. So then what happens here? Minus 2, 1, minus 2? Yeah. 1, 0, 1, 2, minus 1, 1. So the point is, this is the identity, which means we went down here, we got this. So this thing is what we're looking for. So the reason why I like these questions, well, when I was a student, nobody told me this, and I wish someone had, is these are all self-checking. So what I mean by that is if you are told to solve a system of equations using row reduction, you could check your answers, plug it in, should work out. Same thing here. You're told find the inverse. Well, I know that A times A inverse better give me the identity so I can check, right? We can make sure that our answer is correct. So let's do that. check. A times A inverse equals the identity. So we've got our A, which is 1, 1, 1, 1, 2, 0, minus 1, 0, minus 1, times minus 2, 1, minus 2, minus 1, 1, 0, 1, 0, 1. So we just go through the multiplication steps here, right? Minus 2, that's minus 1. I wrote something down wrong. This is a 2. Right? Yeah, it's 2. So minus 2, minus 1, so that's minus 3, plus 2 is 1. 1, wow, did I screw up another?
Yeah.
Oh, wow, I can't. Look, I'm tired. That's a 0 and a 1, right?
And that is minus 1.
Wow, I could not have screwed this up more than I did.
The second rule.
Yeah, everything is wrong. Hold on. Let's make sure. I see what I did. I copied row 1 down from that, and then I started copying down A again. So, oops. Okay. Yes, now those match. We're good. Yeah.
The second row is 101.
But is that a mistake I made here? No. Thank you. Look, we'll get there. Yes. Okay. Everything is working out now. It's all coming up Milhouse. So 1 times 1 is 1. 0 minus 1, that's a 0. Minus 2 plus 1 is 0. Minus 2 plus 2 is 0. 1, 0, 0. Minus 2 plus 2 is 0. So that's 2 minus 2 is 0. Minus 1 plus 1 is 0. That's plus 2 minus 1 plus 1. Okay. It worked out. Once I copied it down correctly. So again, the reason why this is nice is I can just say solve the system x plus y plus z equals x plus 2y equals minus x minus z equals, give me some numbers. Sure. 2 minus 1, whatever, right? So now we can solve this system, where this is our b, right? By just saying x is A inverse times b. So A inverse, we just found that. Minus 2, 1, minus 2, 1, 0, 1, 2, minus 1, 1. Check my work, because I'm apparently falling apart. 4, 2, minus 1. So this says. This will give us our x. So this is minus 8, plus 2 is minus 6, plus another 2 is minus 4. 4 minus 1 is 3, and 8 minus 2, so that's 6, minus 1, 5. That's apparently our answer. This is x, y, and z. So that means if we plug these numbers in for x, y, and z, it should solve this. Minus 4 plus 3 is minus 1 plus 5 is 4. Minus 4 plus 6 gives us 2. 4 minus 5 minus 1. So it works out. Right? But then you could pick any numbers you want here, and it's easy to solve, right? You just do this multiplication and you have another solution. So when we're implementing stuff like this in computers, this is useful, right? If you know the inverse, then just bam, 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 do them out. Because So don't worry too much about it. But row reduction and finding inverses through any method, inefficient. Or not so much inefficient, it's just slow because you have to do a lot of operations. It's n cubed operations. So that means this method really starts to shine if you have a bunch of different columns that have to go in here, and you need to solve all of them, which probably not the case anymore, because now it's probably AI driven. But back in my day, Google's search analytics algorithm used basically something like this, right? It used linear algebra to figure out which search results were most relevant, and how they increased in the rankings and stuff like that. So they would solve a bunch of these a bunch of times. So doing something like this is more efficient, right? You find this inverse once, and then you do a bunch of multiplications, and it ends up being more efficient. Okay, so I have a bunch of properties of inverses and stuff like that, but I don't. These are all things that, if you need them, you will find them. So I just want to talk about some warnings, basically. And then that's the last thing. And then we're done. Hooray. So the first one is you have to write A inverse. And you're like, oh, what do you mean, Travis? Not 1 over A. And if we think about it, if you write this, what does that mean? Is it A inverse times B or B times A inverse? They're not the same thing, right? So this notation is ambiguous. Is it A inverse B or B A inverse? They're not the same thing. So it takes some getting used to, but we do have to use this to avoid that ambiguity. So that's just a remark. Not that big of a deal. I'm not going to penalize you for it. I just want to mention it. If it were a regular linear algebra class where we spent the whole term on it, I would, because it means you don't understand it. These are some things that aren't true for numbers either, but students mess them up a lot. A plus B is not necessarily invertible if A and B are. So that's true for numbers too, right? 1 and minus 1, if you add those up, you get 0. Well, we can't divide by that, even though you can divide by 1 and minus 1. So sure, this makes sense. I have some examples in my notes showing that. But even if it is, A plus B inverse does not equal A inverse plus B inverse, because that's also not true for numbers. So for numbers, so try A equals the identity, B equals the identity. Simple as you can get. Doesn't work. But in terms of numbers, think of it this way. 2 plus 2, quote unquote, inverse. So is that the same thing as 2 inverse plus 2 inverse? We just have to remember what this means. It's just fractions. So 1/2 plus 1/2 is 1. Okay. This here is 4 inverse, which is 1 over 4. Not the same thing as 1. Right? So you can think of this as saying, is this the case? Which, no, of course not. Right? And this would be the same thing for matrices, right? So this doesn't make sense for numbers, so it doesn't make sense for matrices either. That's all I really have for warnings. There is maybe one more example I might want to do on Wednesday just before class to get us warmed up, but that's it. I'm out of math. Well, I'm not. I could look, I could hold you hostage and Clockwork Orange style teach you more math, but I won't do that. Am I the only person who's it? Well, Jordan, it sounds like you've seen it. Yeah. You know it. Anyway, yeah, that's all. So I guess in terms of real quick announcements, so there's no quiz this week because according to the letter of the law, the course outline, there is a chapter review assignment due. I made it due Saturday. I need to double check the course outline. It might need to be due Monday. So worst case, you just get more time. I'll have to check. But I took the quiz I would have given you and just made it that. So the chapter review assignment is like 2 questions.
Okay.
So it's like it's gonna be like the easiest, whatever 7% you've ever earned probably. You'll have to do 2 questions. I guess that also means making a mistake is significant, but I looked, like I said, I looked over the last 2 quizzes. I need to post the grades for them. Everyone did really well on row reduction, so I wouldn't worry about it. It's solve a system using row reduction and then find an inverse. So it's more row reduction. So that's pretty straightforward. That also means that Wednesday and Monday, fortunately, we do have work periods again, just like we did whatever it was after the reading break or before the reading break. I don't remember. We had two classes where it was just, hey, come in and I'll help you with whatever you want. So this is the same thing. I'll help you with whatever you want. So there's a chapter, there's the assignment due Saturday, maybe Monday. There's a group assignment due on Monday, but I've talked to a lot of people about it. It seems like people are mostly already done it. It was everyone was just waiting to hear the inverse stuff in my experience. And then there's the final project. When it comes to a programming project, if you're like, Travis, I'm really stumped on this specific part of my program, I'm getting this weird bug, that's tricky to solve in person. That might be better as an email, so I can actually like test your program and debug it and try stuff out. I mean, I'll happily look at it here, right? I don't mind, because it might be just like, oh, you missed that. But if it's something more, there's like a weird bug happening, then I probably have to actually dig into your code, which it could take me like half an hour, depending on where it is and how widespread it is. So if you want to ask specifically about Project 3, might be better as an email. Again, I'm not going to turn you away. I'm not going to say no, I won't look at it. But it is easier to do that over email where I can actually like debug it and send me your code, by the way. Don't just say, I'm having a problem here. I'll be like, okay, thanks. Just email me your code in a zip file, because I think Outlook at our institute by default blocks Python files. So that's annoying. Or you know what? If you have a specific question about the homework, do this. I have my quote unquote professional email. Gmail won't block it, which is funny. It's exactly what you'd expect it is. You can just email it to me there, and then for college bookkeeping, CC my RD Polytech email so that they don't get mad at me for doing something that's not college related on a non-college email. But our Microsoft Outlook filter will block a Python file. So like if you try to email it to me, it's like, well, how the hell am I going to help you if it blocks it, right? So you need to put it somewhere. So you can just email that, and that's fine. That's my work but not work email. So yeah, with that, I guess I'll see some of you on Wednesday. Again, attendance is not mandatory. So if you're like, I'm good, I will not be upset at you. You don't have to be here.
It means we have just 3